Hi folks, I want to do a quick demo of the Tempel library to give you an idea of what it is, what you would use it for, and approximately how it works. So I've created a demo namespace over here. I'm importing the Tempel library. I'm also importing Nippy, which is used for serialization. Nippy is an optional dependency, but it's useful because Tempel operates on byte arrays. So it encrypts and decrypts byte arrays. And Nippy is one way, one convenient way to convert Clojure data types, arbitrary data structures into byte arrays. So for example, freeze my text. This gives us a byte array. If we look at the content, it's a sequence of bytes. And we can reverse the process like so. Nippy in particular understands all of Clojure's core data types and supports nested data types. So myvec hello set ABC5, something like this, right? You get the idea. So what is Tempel? Tempel is a framework to help manage encrypted data. So what does that mean exactly? I guess we can start with some basic examples of encryption. The easiest place to start is here, Tempel encrypt with password. This is an example everyone should be familiar with. We have some data, we want to encrypt it with a password, we will later on decrypt it with the same password. So this is an example of symmetric encryption. If you look at the docstring, it includes a bunch of info in here. The main thing we're going to start out with is the content. So this is where we're going to use the serialization library like Nippy, freeze, my secret content, and we're going to take a password, my password. So this returns an encrypted payload. We can reverse the process or decrypt it, password, with my password again. And what this is yielding at this point is the serialized version of the data that we put in. So we thaw that, and we get back the secret content that we put in. So this is the simplest example. It's the one that people are going to be most familiar with. We are using a password to encrypt something and decrypt something. I want to already show you one thing which is sort of a bit advanced, but it's useful just to be aware of how this works. So one of the key ideas behind Tempel is that it uses a lot of reasonable defaults. So in a lot of cases, you don't need to think about how it's working. It's just going to work. And the API with which you're interacting, the API that you're using to interact with it is pretty high level. But it is making some choices in the background. And one of the ways that you can examine those choices in a little bit more detail is to look at this var. Over here is the docstring. It's Tempel star config. So it's a dynamic var. The docstring is quite detailed. It explains a bunch of the different options that are in there by default. It explains under what circumstances you might want to change these options. It explains how to change these options. It's not super important. Like I say, the defaults are totally fine for 90% of cases, maybe more. But I do want to point out one thing which can be useful. And we can already look at that in this simple example. When you are encrypting something with a password, behind the scenes, the password needs to be converted into a key, which is suitable for encryption. And that conversion process of converting the password to a key is termed generally key derivation. In particular, password-based key derivation. So there's a lot of acronyms and terminology in cryptography. You're not going to need to know most of those for using Tempel, but there is an idea here which is a little bit important, which is when you are converting from a password to a key, you are going to care about, or rather you should be aware of, the cost of converting that password to a key. Because in most cases, you want that cost to be non-trivial. Because if it is trivial to convert passwords to keys, then it opens up attack vectors like dictionary attacks, where let's say somebody has access to your database and they're going to attempt to brute force possible passwords by running through common words, common passwords, common combinations, things like this. You want to make that brute force attempt expensive, and one of the ways that you do that is by making the derivation of the key from the password expensive. Again, details of this are not important, but I just want to show you one quick example of how you could tune something like this in Tempel. So looking at the Tempel config var, you will notice that one of the options in here that's mentioned is this PBKDF NWF. So that's a mouthful, but basically it is the password-based key derivation function normalized work factor. Again, big mouthful, in practice, quite simple. This describes how much effort it should take to convert a password to a key. The default is marked over here with a star, and I just want to point out one of the things that's a little bit unusual about Tempel and that's interesting is that it allows you to specify the cost, the objective cost from password to key in terms of time. So most key derivation functions have parameters that are quite obscure, and it's a little bit difficult to understand what parameters you should use in which different cases and what the effective tuning of parameter is going to be on the runtime of that function. Again, this is a long, complicated topic. Suffice to say, Tempel tries to simplify this by offering these reference keywords, which is to say, by default, when encrypting with a password, it is going to generate a key from your password in a way that takes 100 milliseconds on some reference system, right? So that's approximately how expensive it is. In some cases, you may want to tune that because you want it to be more expensive. Again, there's some descriptions in here about under what circumstances you might want to do that. But anyway, I just want to explain a little bit how the config works. So you could change the cost of this password stretching by setting the root binding of config or by doing a dynamic binding, or, and this is quite convenient, you just include it as an option right here. So PBKDF, NWF, and then ref, let's say 2000 MSECs, something like that, right? So what I've done over here is I've just included some config directly in the specific API call, and that will now override the default. When I evaluate this at the REPL, I should tell you when I'm evaluating. So now you're going to see it's going to take 4 seconds to run this evaluation because it's doing one key generation during the encryption and then another key generation during the decryption. So it's 2 seconds plus 2 seconds. Again, this is explained more in the docstring for config. It explains in particular under what circumstances you can override arguments like this. But anyway, I just wanted to point that out. Most of the time you're not going to need to do that, but there is a pattern here which is consistent throughout the API, which is the defaults are sensible, but you can examine what they are to understand any trade-offs that might be being made if you want to audit something, or in the cases where you want to override behavior, you do have the option to do that. So on the surface, the API works with a lot of assumptions. They are reasonable, but you can get your hands dirty either to verify them, to audit them, or to change them in the cases where that might make sense to do. So in any case, I've shown you a quick example here, how to encrypt with a password and how to decrypt with the password, straightforward. Good. Let's do something a little bit more interesting. And to do something a little bit more interesting, I want to introduce the concept of keychains. So this is a core concept in Tempel, and it is one of the main ways in which Tempel, I would say, solves many of the problems or attempts to solve many of the problems that come from real world management of encrypted data. So if you look at this is the Tempel wiki, I have in here a section called challenges, and I describe here in some detail what are some of the things in practice that actually make having encrypted data in your application difficult, all right? And this is, in any case, read the text over there. I go into some detail on the kinds of things that are difficult. One of the ways that Tempel tries to solve those particular challenges is through the use of something called a keychain. I will show you how this works. Tempel keychain. Again, everything is documented. Here's the docstring. It explains what it's doing. Basically, when you run this function, it is returning a new private keychain. The keychain, as analogous to real-life keychains, contains a bunch of keys. In this particular case, it contains one symmetric key, 2 private keys, 2 public keys, and there is this secret bool over there just to remind you, hey, this is private information in here. If you def this and eval it, You see the basic breakdown of what's in there. You can also deref it to get detailed information. In particular, this breaks down the name of each key, the type of algorithm that's used, the priority that's used. So all of this information is inherent in the keychain. So what do we do with these keychains? I'll show you a few things. So over here, we've created a keychain. One of the first things that we're going to do, because this will be a very common a thing that you will commonly do with Tempel, is you will encrypt the keychain. So Tempel/encrypt dash, and you'll see here all of this is quite searchable. Encrypt keychain, KC1, and now we're going to put a password. My password. So when we encrypt a keychain, what we get back is a Tempel payload that has serialized all of that information that I showed you before, right? So all of this stuff, the contents, has now been serialized and encrypted with a password using the key stretching, the default key stretching in the dynamic config, all right? Once we have this encrypted keychain, we can do things with it. In particular, Tempel/public data. We can pass it to this public data function. And again, it's documented. The public data function can be used against any encrypted payloads in Tempel, and it will tell you things like the algorithm, any particular key names that were used, schema information, and when looking at keychains, it will give you a public part of the keychain. So let me describe a common pattern which is enabled by keychains and which is very widely applicable and very easy to use. So the pattern is this. When a user creates an account, so let's say Alice creates an account, right? So she signs up, account. We are going to create a keychain for her. So we'll say Alice keychain. I'm going to use a bang over here just to indicate that it's a private keychain. Tempel keychain. By the way, calling keychain in this case is actually using a caching system underneath so that the keychains can be returned quickly. There's actually a keychain generator underneath which is pre-calculating keys because some key creations can actually be quite expensive. So this is doing that in advance and caching some of them. Again, that's all configurable, but the point is Tempel's doing a lot behind the covers to make the practice of this actually quite simple for the common use cases. So you'll usually get an immediate response from calling keychain. So we create a keychain for Alice. It is private. So over here, Alice's private keychain. Don't store. So we've created her keychain, but we need to store something. So what do we store? Alice, I'm going to say encrypted keychain. Tempel, encrypt keychain, Alice KC, and now we can use a password. Alice's password. And I'll say Alice's encrypted keychain, safe to store. Okay, and we've used Alice's password over here to encrypt her keychain. And we can also Alice public keychain, let's say Tempel public data of Alice encrypted keychain. So first thing I'll show you what this looks like. So the public data of Alice's keychain includes a few things, schema information and so on, but in particular it's got this keychain member, keychain, which is the public component of Alice's keychain. Alice's public keychain. Keep this consistent. Okay, so she's logged in. We created a keychain, a private keychain for her. From that, we derived an encrypted keychain and a public keychain. Usually, the way this pattern is going to work is you store the encrypted keychain in your database, and you only keep around the private keychain temporarily while Alice is logged in. So for example, she logs in, you have her keychain, you put it in a session. You retain it in memory. Once she logs out, or once her session expires, you let go of that information. So you keep it as ephemeral information. The idea is you don't want to keep private information stored on disk, so that if there is a leak of some sort, you're not keeping private information around in a way that can get leaked. So this will basically be in our DB. These two things. We'll have Alice's encrypted keychain and we'll have Alice's public keychain. Now we can do the same thing for another user. Let's duplicate this. Bob. All right, and now we're going to do this over here. So I'm just simulating here. We've had two different users sign up. Bob, and we'll keep this the same. Okay, so this is an example of what we might have in our DB under this pattern, right? We've got Alice's encrypted keychain, we've got Bob's encrypted keychain. From those encrypted keychains, we can also at any time derive their public keychains, so the public component part of their keychain. What can we do with that? Actually, turns out quite a bit. This is described in some more detail in the Tempel wiki. In particular, there is a section called the API overview. And as you'll see, it's actually quite short. There's not a huge amount. The main core of Tempel's API consists of 1, 2, 3, 4, 5, 6, 7 functions. That's it. And they're all comprehensively documented. So there is the ability to create a keychain, to encrypt a keychain, to decrypt a keychain, and then a few ways that you can encrypt data using keychains. So I'll show you a little bit of what that looks like for now. So we have in our DB these encrypted keychains and public keychains. What can we do? So one thing we can do, Tempel encrypt with one key pair. And if you, by the way, if you search, Tempel's API is quite browsable. If you do an autocomplete on encrypt, you'll see all the options that you have down here for encryption. So it's pretty easy to see what your options actually are. But in any case, let's start with one key pair. Again, the doc string will explain exactly how this works, what the relevant options are, and so on. What we're going to do in this case, we note first we take the content and then the receiver's public key. So let's do content for Alice's eyes only. And we're going to take Alice public keychain. Alice PKC. Okay, there we are. So what we've done over here, we've taken some content and we have encrypted it using data that is in our database at rest. Alice need not even be online when this happens. And we have encrypted something in such a way that only Alice can access it. So if this data, this encrypted data right here, this is a byte array, if that encrypted data gets leaked at some point, the private information remains private. Alice can access or see the information by decrypting it with her key pair. And over here, you'll see it suggests now we need the private component of that. We don't need to worry about individual keys. We just use her private keychain, Alice keychain. By the way, I've used over here this convention of marking the private keychains with a bang, just to make it very clear these are private, they have sensitive information, you shouldn't be storing them. I might recommend the same convention in your own code base. Somehow mark the private stuff so that you're not accidentally squirreling it away somewhere or logging it or doing something else with it you shouldn't be doing. So here's an example. Again, we are encrypting a private message to Alice using her public keychain, and we are then decrypting it using her private keychain. So this assumes she's logged in over here. And we thought that we get back to content just for Alice. So that's one example of what you can do with Alice's encrypted keychain. A user in your system has an encrypted keychain. You can use that encrypted keychain to send them private messages that only they can read. That's one application. And again, that is explained over here in the table of functionality in Tempel. What about the case where we have, let's say, Bob, and Bob wants to send a message to Alice in such a way that not only can Alice read the message, but Bob can also read the message. So a common situation would be something like a chat application where Bob wants to initiate a chat with Alice, and he wants both parties to be able to read the conversation, right? So again, fairly straightforward. Tempel encrypt with 2 key pairs. Now we're going to use this function. And again, it explains in detail how this actually works. We will always start with the content. So freeze. Hi, Alice. My name is Bob. Right? So that's the content we want to encode. We want to encrypt. First up, we need to provide the receiver's public key. So this will be Alice public key and the sender's private key. So this will be Bob KC. Bang. So this would be available when Bob is logged in. And we encrypt this. And we're going to verify that Alice, when she logs in, will be able to read this message. Decrypt with 2 key pairs. And then we are going to take, let's look at the doc string for this. We're going to take the private part over here, which will be Alice KC, and we will take Bob public keychain. And that gives us the serialized content, which as usual we can thaw, and we get back the message. So in this case, we've shown that we encrypted some content that Alice could read, and now let's confirm that Bob can also read it. So in that case, we're going to flip these two around, and we're going to use Bob KC and Alice PKC. And Bob can also read the message. So in this case, we have over here with the encryption created data that we can store safely at rest. It is inaccessible to anyone except Alice and Bob. So far, so good. So it gives you an idea of the kinds of things and roughly breaks down into symmetric and asymmetric encryption. Again, this is all described in the documentation, a little bit more detail, but it's really not very complicated. I want to go over the pattern in a little bit more detail that I suggest is a useful one for many applications. So when someone creates an account, you create this encrypted keychain for them. You keep the private keychain around in memory just while they remain logged in. When they log in, you kill this information, right? So you let that go. Later on, when they sign in, Alice logs in. What you're going to do at that point, Tempel decrypt keychain, Alice encrypted keychain, password, Alice's password. At that point, you're going to, during the login, you're going to take Alice's password again. If it is the correct password, it will yield Alice's private keychain, which means you can immediately sessionize it, you can keep it around in memory, allow her to interact with your system, to interact with the rest of Tempel's API, to do all the kinds of encryption or decryption that you might like to do. And again, when the session expires or she logs out, you let go of that information. What happens if she gives the wrong password? If she gives the wrong password, this will return nil, which means you can easily incorporate this into your usual login flow, right? You're going to take the user's password, you're going to try to decrypt their keychain. If it's successful, you know that they've got the right password, and they can now interact with the rest of the system. And if it's the wrong password, this will return nil, in which case you give them an error message, you do your rate limiting, whatever you want, the usual stuff. What happens if Alice forgets her password? One of the benefits of the pattern as I've described it is that all of our sensitive data is encrypted at rest, which is the whole point of what we're doing here. The downside of that is, of course, that if Alice forgets her password, now all of the data which has been encrypted using her keychain is now inaccessible, right? So this goes back to if we try to decrypt keychain, Alice, EKC, password, wrong password. So if this doesn't work, she doesn't know her password anymore, how do we get around this? Well, one way, a common pattern that I would often suggest is something like this. So we're going to have admin keychain, admin's private keychain, don't store. So just like all the other cases, Tempel keychain. And we are going to create an admin encrypted keychain, just like all the other cases. keychain, admin's password. So we're starting by creating another account, just like we did all the other accounts. This one is intended for admins. This is an example of one of the cases where we might want to change the cost of the password stretching. The F work factor, F2000 MSEX, something like this. So here we are bumping the default cost function we're bumping the cost function from the default 100 milliseconds to 2000 milliseconds. By the way, if you mistype this or something, if you put in an option that doesn't make sense, it will complain, so you'll know while you're compiling, and it will tell you what the valid arguments are. So in any case, we've created an admin account over here. We have the admin's encrypted keychain. How do we use that? So one of the ways that we can use that is when we are creating the accounts for other users, right? We are going to use a feature in all of the encrypt tools, which is labeled over here backup key. So first, let's do this. I want an admin's public key. Admin, public keychain, public data, admin EKC. So we have the admin's private keychain, it's encrypted, and we have the admin's public keychain. And over here, we are going to use, my screen is having some problems here. We are going to use the admin as backup key. So admin PKC. Backup key, admin PKC. What this means is when we are creating Alice's account, when we are creating Bob's account, when we are creating other user accounts, the admin's public key is being used as a backup, which means if Alice ends up forgetting her password, it is possible in that case for the admin to log in, giving us access to the admin's private keychain, and using the admin's private keychain, they can actually decrypt Alice's keychain, which means we can reset her password. And actually this brings up another point which is important, which is one of the advantages we have in this approach is that passwords and keys are not actually coupled together. You'll notice that passwords are used to decrypt your keychain. So over here, Alice is encrypting her keychain with her password, and then later on, decrypt keychain, Alice, encrypted keychain, password, Alice's password. So this is on login. The password is only being used to unlock the keychain. The keychain is what's actually being used, and the keys inside the keychain are what are actually being used to encrypt all the data. Which means if we want to change Alice's password for any reason, we can change the password just by changing this over here. We're changing the encrypted form of the keychain. The actual underlying object which results the unencrypted form of the keychain remains the same, which means basically we've decoupled password changes from key changes. It is of course still possible and sometimes necessary to rotate keys, but rotating keys is rarely needed. You only are generally going to rotate keys in the case where you think a key may have been compromised or there's some other reason that you want to get rid of a specific key, whereas password changes happen all the time. And it's a nice property to be able to change the password without invalidating all of the data or re-encrypting all of the data that was encrypted under a different key. Likewise, I want to point out that one of the things that Tempel does, which is unusual and very, very helpful in this data management aspect of running an encrypted application, is that any kind of payload that Tempel produces, so for example, Tempel encrypts with symmetric key. This is one I don't think I've shown yet. Freeze secret content. And we will use over here Alice Alice's private keychain. So when we produce this data, this is now an encrypted payload. It's a byte array. All payloads generated by Tempel can be passed to this public data function that I showed you earlier. And again, there's information in the docstring explaining what the possible values are. But the way that this works is every time Tempel is producing an encrypted payload, it is also prefixing the payload with public information about what algorithm was used, about parameters of the key generation, about any kind of information that may be necessary later on to decrypt the same data. And one of the things that becomes most difficult when actually having an application that really does encryption, right? One of those kind of practical challenges that I mentioned in the wiki is managing stuff like today we're using a particular key derivation function. 3 years from now, we realize that actually computing power has increased and the previous work factors are no longer sufficient. In other words, the cost of password stretching has come down due to improved hardware. We now want to increase that, or we want to change the algorithm because a flaw was found in the old algorithm, or there's a newer, better algorithm, or the cipher algorithm maybe has been deprecated for some reason, or it turned out there was a flaw in that. The point is, over time, the ideal algorithms are going to change, the ideal parameters are going to change. That stuff is not fixed. And if you are changing your algorithms and parameters over time, one of the things that you find in practice is that it becomes a nightmare to make sure that you can always access all of your older information, right? Your legacy information that was maybe written with the now deprecated algorithm or the now deprecated key stretching approach, and so on. And one of the benefits of Tempel's approach to prefixing all of its payloads with this kind of necessary information is that it makes it really easy to treat the keychain as almost as an identity object of some sort, and less as a. You need to be less aware of the details of what kinds of keys are in there and exactly which one is going to be used to do a particular job. You may have a keychain which has 20 keys in there, some of which are for algorithms which have since been deprecated and will no longer be used for generating new data. But maybe you want to keep around the private keys in that keychain so that you can still access data that was previously written before the deprecation occurred. Keychains will take care of all of that because when you try to decrypt a specific payload, Tempel is going to inspect all of this public meta information about what kind of key to use, key identifiers if necessary, and so on. And it will take your particular keychain and it will pull out the necessary things that it needs to get the job done, essentially. And what that means is that in practice, a lot of these kinds of management problems more or less go away. In general, the idea is that Tempel is designed to try and make it easier for more applications to protect their users' data. Getting that right in practice is often very difficult. And the truth is that if you get it wrong, you are either going to introduce vulnerabilities, in which case the data is not actually protected, it's not actually safe, or even worse, you lose access to the data because, for example, you used a key, you've since lost the key, because key management is difficult. Now you can no longer encrypt that data, so the data is effectively gone, it's lost. Getting all of that kind of stuff right can be very difficult in practice. Understanding what kind of algorithms to use in what kinds of circumstances, that can be difficult. So anyway, high level, the idea here is that Tempel is designed to encourage more application developers to consider using encryption as a normal part of their application design process. It takes away a lot of the kinds of complexities that you'll often need to deal with if you're trying to implement all of this stuff in an ad hoc fashion, or if you're using a low-level toolkit which just provides, different algorithms and different parameter options. Thinking about all of that and trying to figure out when should you use the different algorithms, when should you tweak these parameters, can be quite difficult. Additionally, figuring out how to maintain all of this stuff over time can be very difficult. And the idea is that Tempel makes both of those kinds of things easier for the common case where you don't particularly care to do something highly complex and highly unusual. Instead, a simple pattern like the one that I've described will let you do everything that you need to do and is robust, is easy to implement, is not particularly complicated, and doesn't require any particular customization because the defaults are totally reasonable for most users. So anyway, that's the idea behind Tempel. Hopefully this demo gave you some idea of how it works. There is a lot more information on the wiki, usage information, examples. There's an FAQ. If there are particular questions that maybe the documentation doesn't address, do let me know. I'm interested in improving this stuff. And again, one of the main motivations behind this is really trying to encourage more application developers to at least consider encrypting their user data when possible. It is often possible, and it is often possible in a way that is actually quite easy and is actually quite secure and is not difficult to maintain. Even if you just implement encryption for the most obvious easy places in your own application, that can often make a big difference and will already be significantly better than if no encryption had been used, if no data security were in place. And yes, that's the idea.